Hi everyone. This is the third presentation of our class. It's called Carbon Dioxide, Societal Development, and Energy Resources. I want to start by having us realize that when we burn non-renewable energy resources such as coal, petroleum, or natural gas, we unavoidably produce carbon dioxide. It's a necessary byproduct of the combustion event. Now, non-renewable energy resources are called hydrocarbons for a reason. They all contain hydrogen as well as carbon. When we ignite these to power our modern lives, the hydrogen and the carbon are chemically recombined with atmospheric oxygen. So in the second bullet down, we see carbon's chemical bonds break during combustion. The chemical bonds are nothing more than the electrons being shared with electrons of other components in the chemical formula. Okay, so carbon's chemical bonds are broken during combustion, and the freed carbon atoms bond with atmospheric oxygen. Now, this also happens with the hydrogen and any other atoms that happen to be in the fuel. I have an example here of methane, one of the simplest hydrocarbons available. So that's chemical formula for methane is CH4, and when we combust this, we combine it with two molecules of oxygen. And so we have that large number 2 and the small O2 there, and that is the way we symbolize two molecules of oxygen. So we have one molecule of methane, and that chemically recombines with two molecules of atmospheric oxygen. And what we get from that chemical reaction is two molecules of water vapor. That's that large 2 there, and next to the H2O. So that's just water vapor, and that's benign. That goes into the air, and that essentially is the same thing as humidity. Nobody really worries about that because it's just water vapor. Okay. We also get carbon dioxide, one molecule of carbon dioxide, and that also goes up into the air, and we are increasingly concerned about that. And then we finally also get the third thing, which is what we want, and that's energy. And that can be in the form of heat and light. So when you burn something like coal, you can see it burning, but you can also feel it burning. And that heat that we feel is, of course, what goes on into boiling water that spins a turbine, that spins a generator, that finally generates electricity. So we don't really care much about the water vapor. We are increasingly worried about the carbon dioxide, and we really want, of course, the energy. Now, in our atmosphere and in climate and meteorological science, we measure carbon dioxide in a unit called parts per million. And we abbreviate that oftentimes with the small letters ppm, parts per million. Sometimes you'll see this abbreviated as ppmv, and that simply means parts per million by volume. ppm is shorter and it's more convenient, so we're going to use that. They essentially mean the same thing. So we know from physical records that over the past 650,000 years, well before humanity ever arrived on the scene, Earth's atmosphere naturally contained somewhere between 180 to 300 parts per million of carbon dioxide. And this tends to vary. So we can track this as Earth's millennia pass, and sometimes we have more and sometimes we have less atmospheric carbon dioxide. But it's always stayed within this range between 180 and 300 parts per million. And that's been for the last 650,000 years. We also know that right before the Industrial Revolution, and depending on how you measure this, you can say the Industrial Revolution started around 1750 or 1775 or somewhere in there. But right before this, we know that Earth's atmosphere had a ppm of carbon dioxide of 280. So 280 parts per million. And that fit nicely within the last 650,000 year CO2 ppm range. Now, however, we have noticed and we've measured and seen, and it's causing some concern, that Earth's carbon dioxide ppm is now 398 parts per million. And that is greatly exceeded the last 650,000 years, and it continues to climb. Okay, so right now we're looking at then Earth's atmospheric carbon dioxide content being greater than the last 650,000 years and rising at an increasingly steeper rate. This chart here is perhaps the most famous chart that has tracked carbon dioxide, and this is called the Keeling Curve. It is named after Dr. Keeling, who began measuring carbon dioxide at the top of Mauna Loa in Hawaii back in the mid-20th century. Notice the y-axis has parts per million, and we could just have abbreviated that ppm. And down near the bottom we have 320 parts per million, and up at the top we have 400. On the x-axis we have years, and they span from the middle of the 20th century to present time. So we have within the chart then two lines. One is a red squiggly line, and one is a dark black line. The red squiggly line is squiggly because during the summer months in the northern hemisphere, Earth's vegetation grows and expands. And that means then that during a normal plant's life, carbon dioxide is absorbed by the plant and then used with photosynthesis to fuel the plant's growth. As the northern hemisphere gets colder during the autumn and winter months, these plants go dormant or die off, and of course, plant's ability to absorb carbon dioxide decreases. And so the red line illustrates that. And notice there's this regular up and down motion of this line as each decade passes. And when the red line is peaking, that means that carbon dioxide is at its peak for that particular year, and that coincides with late winter, when basically all the vegetation, especially in the northern hemisphere, is dormant or very diminished. When the red line is at its base or trough level, the lowest part during any particular year, that means the plant life is really thriving and doing a good job of taking that CO2 out of the air and putting it into plant growth. So every year you can track this, and it's a very predictable and observable event where this red zigzagging up and down kind of pattern exists. If you draw a trend line through those zigzagging red lines, you can see then what's going on an average. And that then illustrates that we have in the mid-20th century parts per million of carbon dioxide in our atmosphere of less than 320. And now in present times we have parts per million of carbon dioxide in our atmosphere approaching and soon exceeding, by anyone's estimation, 400 parts per million. This has caused some concern because, as we'll see in the future presentations here, that increasing levels of carbon dioxide can do pretty powerful things in terms of retaining heat in Earth's atmosphere. All that and much more is coming up in the next few presentations.